Okay, a very good morning to you all, and what we are going to do in this class is I am going to talk about what I have covered in the last class very briefly, and then we will introduce an interesting topic which is microscale manufacturing practices. Now, manufacturing of at microscale could be totally different from what we are familiar with, the macroscale manufacturing processes. Not only the practices are different, the philosophies, the concepts are different as well. So, we would see the two prevalent philosophies in micro machining, micro manufacturing, which one is important, which one is becoming important, and whether or not we can totally shift to one of those. In the later part, we would clarify certain terminologies, for example, numbering up of a system, scaling up of a system, and so on, all related to microscale. And finally, we will have two examples of using specific machining techniques so as to obtain devices, and the two devices, one is going to be for heat transfer large scale. So, even though the heat to be transferred is quite small, the area from which it is to be transferred is quite large, as a result of which the heat flux is very large. So, how to handle situations where a high heat flux has to be removed from an object. And the second one is depending on the surface properties, depending on the manufacturing process that a specific substrate has gone through, the fluid flow, formation of bubbles, phase transfer, weighting, all are going to be different. So, if you think of an experiment in which we have a hydrophobic surface and a hydrophilic surface, a surface which is smooth compared to another surface, how would the phase transition on such a surface take place, and how is it going to affect the pressure drop, and so on. So, we will have a mixture of certain theories, concepts so to say, and applications in today's class. But before I begin this class, I would like to quickly review some of the things which we have covered in the last class pertaining to mass transfer. We know that there are two things totally different at microscale. One is the length scale, which could be microns or even smaller than that, and the second is the time scale, which in a microreactor could be milliseconds. So, we have said or understood in the last class that we will probably use or we will probably opt for microreactors if it is a fast reaction. A slow reactions would require a larger length of the micro device, which may not be possible to fabricate. We may have the technology, we may know that the mass transfer resistances even for slower reactions could be handled by a microreactor, but the limitation of length, you cannot make a channel, micro channel, which is of meter length. At the most you can go for few centimeters. So, how do you do that? You cannot have a slow reaction in a microreactor. But there can be situations in which combined reactions, when you have the principal reaction which is relatively fast and the other reactions, undesired side reactions, slower, then an effective use of a microreactor can give us better yield of the system. And finally, since it is very small, since all the transport processes are taking place within the boundary layers, within a thickness which is comparable to the boundary layers, any reaction which is highly exothermic or any reaction which has dangerous side reactions, so that the heat has to be dissipated, they are prime candidates for microscale reactors and so on. So, we know that mass transfer limited reactions are well suited for microreactors, and it has been shown that generally the sizes of the microreactors are approximately 200 micron. Okay. It can vary from 50 to 500 micron, but the optimum size of a microreactor will be of the order of 200 microns. So, we have to keep that in mind, 200 microns and a few centimeter in length. So, how do you combine such channels together, ensure uniform flow through them, and to have a system which would give you at least measurable quantities of the product. That is the challenge. So, that is the manufacturing challenge, that is the fabrication challenge. So, we would see what are the practices which are followed in such cases. So, two views of micro or in nano manufacturing. Okay. So, one is top down process, the other one is bottom up process, one just the reverse of the other, it seems. How many of you have visited Ellora caves? Some of you, all of you have heard about it. Okay. There is a specific cave which is world famous in Ellora, the cave number 16. Anyone having idea of what is the structural uniqueness of cave number 16 or any cave in Ellora? You start at the top. Okay. You start at the top of the hill, and the artisans this start cutting from the top and slowly reach to the bottom. So, when everything is finished, all the material is removed, then you have a temple or some specific shape. Okay. So, that is one of the philosophies. So, you can think of how much material has to be removed, how much planning has gone into it, that you are going to have a specific shape, a structure, or maybe something from a like a pictorial representation of some mythical event and so on. So, what is the difference between the construction of Ellora caves and your body? A human being, is there any difference between the concept or between the practice of making Ellora caves and a human organ, a human body at such? A human body starts with what? Just one cell, okay? And from one cell the cells assemble, you create something else, slowly an organ will evolve, okay? A human being, our body will be formed. So, if you think about these two approaches, they are the prime examples of top down process and bottom up process. So, top down process is when you start at the macro scale with a very large rock, as in Ellora cave. Okay. And you proceed to create fine features by somehow processing the bulk of the material, removing the material which is not needed, and finally come up with a structure, well, which all of us can see and enjoy. On the other hand, if you think of bottom up process, it starts at the smallest possible scale. Okay. The atoms in a reaction, cell for living organisms and so on. And it adds complexity to the entire object up from the cell and above. So, processes are controlled by self assembly. I will come back to this number of times. Some of you are familiar or should be familiar with self assembly. I hope. Any idea anyone with some idea of what is self assembly? Okay, does not matter. I also know very little about self assembly, so it won't matter. We would see what is self assembly and how it is going to be the building block of a bottom up process. Now, it is very expensive, top down processes. Bottom up processes, we do not know how expensive it is going to be, but we know it is going to be extremely complex. So, let us see what are the problems associated with top down process, the advantages of top down process and so on. This figure tells you about the examples of a top down or a bottom up process. If I see the left hand side of the figure, we know what is lithography. Okay. So, I will talk about lithography in this course many times. So, lithography and microfabrication, with our knowledge from chemistry and embryology, these two are going to meet somewhere. Where and when we do not know, but right now we are working with lithography, and we also are starting to know a little bit more about the chemistry involved in self assembly and in the bottom up fabrication. So, the top down fabrication becomes harder and harder, and it is becoming more and more expensive, especially when the device sizes are becoming quite small. Okay. So, the smaller the size, ultimately we are going to be limited by the wavelength of the light that we are going to use. because your lithography or photolithography depends on the wavelength of the light, and there is going to be some diffraction, and ultimately the wavelength you cannot go below that. It is difficult even to approach that. The size limit that has been achieved is 65 nanometer. Okay. So, let us say 100 nanometer. So, you cannot go below 100 nanometer with the devices, with the equipment that we have today. Whereas, on the other hand, if you think of the bottom of fabrication process, if we can do it, then you start with at the angstrom level and grow up from there. So, bottom up fabrication is definitely harder to design, and something like self assembly will require self assembly. I will give you an example of top down approach which has been performed. It is a very basic operation, but since we have done it, I would like to advertise it. Let us say. So, it is fabrication of a V groove on silicon wafer. Many of you are aware of what is a silicon wafer. So, you start with this is the gray one is the silicon wafer, you grow an oxide over it. So, silicon dioxide, coat the silicon dioxide layer with some photoresist. So, when you expose the photoresist to ultraviolet light, there would be some chemical reactions, there would be cross linking, and depending on whether it is a negative photoresist or a positive photoresist, it may get hardened or may remain as it is. So, you make a mask. Mask is something which is a negative of the structure that you would like to imprint on the surface. So, the mask will allow UV rays from some portion of it, mask will allow the UV rays to pass and interact with the photoresist. Okay. So, there will be some portions of the photoresist which would be cross linked, which would be hard in this specific case, the rest will remain as it is, which would be easier to dissolve away using the right choice of solvent. So, now you have islands of photoresist, you now remove the oxide layer as well. So, here you have the silicon, exposed silicon, and some portion of the silicon which is not exposed, which is protected by silicon oxide. So, you have achieved the first part of your objective, that is you have imprinted you have protected the areas where you do not want to etch any silicon, remove any silicon, expose the areas where you would like to do something. So, the next step would be use a silicon etch, which would be a concentrated KOH solution at elevated temperature, roughly about 85 degrees or so, and depending on the crystal planes it is going to etch. So, depending on which type of crystal, 100 or 110, whatever crystal of silicon that you are using, they are going to etch, and the two crystal planes will propagate and meet at certain point, and the etch becomes self stopping. So, the etching rate at different crystal planes are different, okay, vastly different. So, it is going to etch only in the vertical direction, but it cannot go in the side direction. So, what you end up is nice V grooves on silicon wafer. Once you achieve that, you remove this oxide layer as well, and here you have a silicon wafer with micron size V grooves of certain length on it. Okay. So, roughly the dimension here is about 30 to 50 micron, the one that was done here, and the length of this is about 2 centimeter. Now, this has been used for some purposes, which maybe some other time I will talk about, but this gives you an idea of a top down approach. You start with the complete material, remove part of the material, and end up with a structure, end up with a micron size structure. Now, what are the things that you have to use in this process? You definitely require a lot of chemicals, you require specialized instruments which are prohibitively expensive, and it's we do not have the latest one, and it's any kind of fabrication has to be done at a controlled environment where there are no dust particles. So, you will hear facilities like class 100 atmosphere, in which you have the class 100, I think the definition is there would be less than 100 particles of 10 micron size or more in 1 cubic meter of air. So, there will be filtering of air, specialty chemicals and processes to clean the silicon and so on. So, we see that it is becoming more and more a process which more and more of a process which requires a lot of money and investment and specialized training. And if you look at this specific graph which I have got from somewhere, from 1970 till 2010, close to 2010, okay, the number of transistors on a chip, it is increasing phenomenally. Okay. So, right now we are somewhere around here right now, and the problems associated in packing so many transistors on a silicon chip, obviously the cost of newer technologies and physical limits of photolithography that I have discussed, this is the one which I have not talked about. Any transistor is going to generate some amount of energy. Such a small size transistor will generate very small quantities of energy, but the areas are going to be so small that the heat flux to be removed in order to maintain the temperature of the chip within allowable limit of about 80 degrees centigrade will be enormous. So far the cooling technology that is being used is just convective cooling, okay, fan, number of fans and so on. There has been propositions of liquid jets to cool the chip or other techniques, but all the newer techniques involve change of phase heat transfer, because when a change of phase takes place, you are going to extract the maximum amount of energy. It is going to be much more than convection, much more than normal convection, conduction or any other process that you can think of. So, how to have a proper cooling technology to dissipate the large amount of heat, that is becoming one of the major challenges of top down approach. Now, let us think of a bottom up approach. Okay. You selectively add, you devise your strategy in such a way that you can add atom by atom on a surface, on portions of a surface, and thereby build a structure from nothing, out of nothing. So, first advantage is you are not going to lose any material. Okay. You are not going to lose any material, the amount of chemicals involved will be less, since you are not going to depend on photolithography that much. So, the costly equipments, optical equipments may not be necessary, and it is something which happens in nature all the time. So, if you think of cells, growth of any crystal or ourselves, we all have grown using a bottom up approach. This is an example of making of nanodots on silicon, and we will see what is the advantage of nanodots having to have on a silicon. There are certain polymers which have a peculiar tendency that they are going to combine with each other at the molecular level, and they will follow a specific structure, and they will remain at that structure for quite a length of time, and they are inert. Once you make them, they are inert. So, you can start the process by selectively exposing certain areas for these for the growth of these self-assembled polymers. So, here is an example that you have 65 billion nanodots per square centimeter. So, since we are talking about molecular level, so you can have surfaces by proper treatment of the surfaces, you can make certain points where the nanodots, where the self assembly can take place, and some points where it cannot. This is not futuristic technology, it is already here. So, what are the advantages of self assembly and bottom up approach? Definitely you can make a much smaller geometry than that is available in photolithography. And we hear about carbon nanotubes, silicon nanowires, which are going to be the material of tomorrow's products, tomorrow's manufacturing, and all are made by a bottom up process. So, if I like to define what is self assembly, so it is the coordinate action of independent entities. The independent entities could be a molecule, could be a cell, to produce larger, and this is very important, ordered structure, and maybe it would lead to a desired shape like you or me. So, this is the self assembly process, and there are various examples of self assembly in terms of silicon processing, like formation of silicon nanodots, nanowires, and nanotube transistors. Okay. People talk about more exotic applications, but I am not going to talk about that right now. The applications, the basic applications that I am going to give you an example is would be optical devices and memory. How? So, again, and picture of a nanodot surface, 10 trillion dots per square inch, and just think of each nanodot holding one bit of information. So, on 1 square inch of surface, if you can make the nanodots, and these are from the AC, I do not know which how they took the picture of this, how much information can be stored using a self-assembled nanodots. Okay, so we are going to finally summarize between the top down and bottom up process, in the sense that if you have top down process, you start with a bulk wafer, a silicon wafer, and then by some process you are going to apply a layer of photoresist on top of it, and the photoresist will be exposed to UV rays in this through a mask, and etch the wafer in order to obtain certain areas which would be protected and certain areas which are not going to be protected. So, the etched wafer then will be subjected to other processes. The example which I have given you is the reverse of this, where we have etched something. In this specific case, we have made 2 pillars on the silicon wafer. Now, let us say we are going to do the same thing using bottom up process. For such a process, you again start with a bulk wafer, but you do not remove any portion of it. You alter the area of the wafer, which is a topic of very active current research, where the structure is to be created. You can add polymer, you can seed with certain crystals or some other techniques, and then you grow or assemble the structure. These two are going to be the reverse. I mean, it should be pointed outward, and so it will again look like this. So, you do the same thing using a top down and a bottom up process, and similar results for some of the cases, similar results can be obtained between a top down or bottom up process. Okay. In the summary, I can say what we can say is that presently top down is still the method of choice for now, at least, and newer technologies are coming up which is severely testing the limits of the top down process, especially in terms of cost, in terms of how small you can become, and in terms of operational ease, for example, heat transfer and so on. People are trying at this moment to use a combination of the two, top down and bottom up process, to simplify the fabrication, and the methodology by which such bottom up approaches can be successful. The key word is self assembly. Okay, so you let molecules form a group, form a structure, grow a structure, and how small you can become on a molecular level, that is going to decide about the future of bottom up process. Now, we are coming to something which is with which we are very familiar with. One is the scale up. Let us concentrate on the right side of the picture. So, what we have is some reaction, some process which is taking place in the laboratory. Okay, you would like to scale it up to a pilot scale first, and then to a production plant. The process involves maintaining certain conditions the same between the laboratory and the mini plant. Okay. So, we know that there are geometric similarity you have to maintain, as well as dynamic similarity. Okay. So, in order to maintain similarities between these two processes taking place at vastly different scales, you maintain the pressure, temperature and concentration constant in both the cases. Not only that, such that the processes would be governed by similar laws or correlations, you maintain the similarity parameters, for example, Reynolds number, Nusselt number, Prandtl number, etc., the same in all processes. So, your concepts that you have envisaged at the laboratory scale would first be transformed into the mini plant level, and using the standard scale up procedure, it would come to the production level. The situation is slightly different when we go at the microscale manufacturing or scale up involved at microscale manufacturing. The first thing you start with at the laboratory, you make one channel, just one channel somehow you make, and you try to perform the same reaction or same operation in that micro channel. So, you work with different geometries first to see where you are going to get the maximum benefit. So, this design part is going to be important. Okay. How do you design it? Okay. Whether it is going to depend on geometry, whether it is going to depend on the nature of the surface that you have, whether there would be number of interconnects in between such a channel and so on. Once you are satisfied with the reaction taking place, a tiny volume of reactants and products being formed in such a micro channel, you go for a process which is known as the numbering up. You just add thousands and thousands of these micro channels in order to obtain some sort of an equipment, which could be a micro reactor, which could be a micro heat exchanger, and so on. Okay. So, there would be problems associated with numbering up. Okay. While numbering up, you have to how are you going to ensure that the same amount of liquid or same amount of reactants will pass through each of them. Okay. How are you going to ensure that there won't be any leakage or any short circuit in between two channels and so on? How do you cover up the channels? How do you design a manifold by which equal distribution is possible? So, these are some of the issues that one has to think while numbering up. So, you can make an optimized structure at the laboratory scale of one channel, but how do you convert that one channel into thousands of channel? The numbering up is going to be a big challenge in such a process. This is the same one with the problems highlighted. So, what you have on one side is we have in the laboratory, and we have two ways to go. We can either go towards the microstructured device part, or we can go towards a standard large macro scale equipment design. So, when from the laboratory, first is, as I mentioned, you first design something of some dimensions and so on. So, this design now has to be stepped down by the available fabrication technology to a micro channel. So, from that fabricated micro channel, you perform the numbering up and you go to a series of micro channels, I mean number of micro channels probably connected in parallel. And these are some of the distributors, flow distributions that one can think of, which are in use, some sort of manifolds, fluidic manifolds which are in use, so as to distribute the liquid evenly through all the micro channel. So, let us go to slightly in more detail. Now, in a conventional way, you start with mini plant and you end up with a big production facility, which is the right hand side of the picture which I have just shown you. From there, if we like to think of the basic elements of a microstructure device, those are going to be the channels. Okay. So, you decide about the minimum number of channels that you would require for performing certain operation. You have to be careful about the process conditions and whether or not you have fabrication technology available that can take care of your requirements. So, this process is known as equal down. Okay. So, a small channel dimensions, the smallest possible channel dimensions are determined depending on what is available to you, whether or not heat and mass transfer and the chemical kinetics, which one is which dimension you would like to reduce. Are you going to reduce the length, or are you going to make the two walls very close to each other, because these are going to give you fundamentally different conversions, for so to say. So, if you have a catalyst surface, then you would probably like to bring the catalyst surface as close to each other as possible, such that the reactions are taking place within the boundary layer itself. Okay. The diffusion of the product to the mainstream would have the least amount of path to go. If you have a very fast reaction, then you probably do not need a 2 centimeter channel. Okay. Maybe half a centimeter would be enough for the reaction to complete. So, your fabrication technology, your kinetics and your heat and mass transfer would govern the size of the channel to be decided in the equal down process. Next is we concentrate on internal numbering up. Okay. So, when you are successful with the experiments taking place in one such microchannel, you try to increase the number by increasing the number of elements which increases the flow rate. And these are some of the enlarged version of the manifolds, the flow distributions which are being used. So, the velocity of the inlet flow is usually directed towards the side walls, not to the entry of the microchannels. Okay. So, if you have the flow directed towards the entry of the microchannels, then the chances are that one of the channel is going to be highly irrigated compared to the other channel. Okay. So, the flow jet is never directed to the microchannel, it is always directed to a side wall or a side plate, such that you have very well mixed high pressure side at the inlet, and then all the channels are hopefully fed with the same flow rate. Okay. So, you decide about the manifold obviously based on the number of channels that you have, and it's still not a complete science where one can explain how to design such a manifold. Okay. So, it depends even now on experimental practice. The key parameters are then the geometry, the fluid dynamics, mixing, kinetics and heat management. Everything we would like to happen at a length scale which is, let us say, of the boundary layers. I will go to an example right now, an example where fabrication that we have discussed so far, the top down approach, has been used to design a heat sink. In this design of heat sink is necessitated by the requirement of high heat removal rates, and as I mentioned, it has to depend on phase change heat transfer. And another advantage of phase change heat transfer is the heat transfer takes place with a very small value of delta T. If you think of a heat exchanger, the delta T's could be of the order of 10s, 20s and 30 degrees centigrade, but when you have phase change heat transfer, you require very small delta T, so as to have a so as to have a phase change. If you think of a thin liquid film, for the liquid film to evaporate across the liquid vapor interface, it has been calculated, it has been shown that the temperature requirement could be as low as 10 to the power minus 3 degree Kelvin. So, with that smaller heat, that smaller temperature jump, you are going to have phase change from the liquid to the vapor or vice versa. So, any phase change heat transfer, any heat pipe, so to say, which is acting on phase change, can operate with smaller, very small delta T compared to a normal heat exchanger. So, these are the experiment that I am going to describe would be very important for flow boiling applications in which I have flow and simultaneously there will be transfer of phase, and the bubble which is formed is going to depend is going to move with the flow, and thereby create two phase flow situations which could be unique in nature. So, let us see what has been designed in this case. So, we have a small microchannel which is made by two glass plates bonded to each other, and there is a micro heater, the yellow part, which is going to act as the hot spot, and I am going to have flow of water from my left to the right. Okay. So, the flow takes place over the micro reactor, and there would be a microscope with a high speed camera which would focus on the micro heater. So, initially when the micro heater is off, then you are simply going to have single phase flow, just flow of water, nothing else, you will not see anything. But the moment the micro heater is on and the heat flux to the micro heater is progressively increased, there will be initiation of boiling. So, the initiation of boiling will create a vapor bubble, and when you supply enough heat, the vapor bubble will detach from the surface and will come to the bulk flow, and it will be carried with the bulk flow towards the outlet. So, this is a situation which is common at macro scale, but at the micro scale we would like to see on what are the factors on which this boiling or the heat transfer would depend on. One obvious factor is the heat flux, the nature of the surface, and so on. So, essentially the setup that we are describing is a Pyrex glass and with a hydraulic diameter of about 56 micron. So, we are in the micro scale, definitely not in the nano scale, and we would like to see the impact of the size of the micro channel and mass flow rate on the boiling phenomena. So, let us see what we get. The first thing that you would get, some of you are probably taking two-phase flow in this semester as an elective course. There you know that the flow regime in two-phase flow can be divided into a number of distinct categories. The simplest one is bubbly flow. Okay? You generate one bubble and that bubble will grow in size. At some point, due to surface tension, it will detach from the surface and it will be carried with the flow downstream. This formation of bubble essentially takes sufficient amount of heat from the hot spot because of phase change, because of latent heat. So, that is the simplest one can think of, and this is a video of this bubbly flow, which obviously is not working. What you would see, if you could see, you have to trust me, is that the bubble will form, the bubble will detach itself from the surface and very quickly it will flow through the channel in the downstream direction. So, they have taken the picture of the bubble, they have measured the temperature, when the bubble forms, when the bubble detaches, and so on. The next one, I will not show the video, then I will describe it. If you increase the heat flux, so what you are going to get is wavy flow of the bubble. Okay. The bubbles become elongated, they are larger in size, and they are still attached as if by ropes to the point where the bubble has formed and progresses in this direction. Obviously, after some time they are going to be sheared off either from their base, or it is going to be cut off from some point around the middle, and will flow with the water flowing downstream. The amount of heat that is transferred by this type of flow, wavy flow, is going to be more than that of the bubbly flow, and this is more difficult to handle mathematically. The next one is annular flow. An annular flow is similar to wavy flow, but here you are going to have a distinct flow pattern of two phases flowing simultaneously side by side to a large length, filling a large length of the pipe. So, you are going to have a vapor core and a liquid which is flowing along the side. Okay. So, the heat transfer, if you calculate the value of the heat transfer coefficient, will be less than before, because this section is more or less going to be covered with a vapor film all the time. So, this annular flow is also going to be seen at some point. Now, we need to have some ideas about when and what type of bubble formation you are going to get on a surface, because you would like to create a surface where it would be very easy to form a bubble. You would also like to see what would be the effect of different machining techniques. That means, whether or not this formation of bubbles are going to depend on the geometry and how they are going to affect heat transfer. So, the trend of research so far was create a new surface of some roughness, make it hydrophobic or hydrophilic, supply some amount of heat flux, let the bubbles form, heat transfer take place, and try to see what is the optimum, at which point you are going to get the maximum amount of heat transfer. So, the trend is for different flow geometries, different structures, when you are going to get the maximum heat transfer. but something else could be thought of, which I am going to show in the last few slides. We know that if we change the surface characteristics, they change the solid liquid interfacial characteristics, which in turn changes friction factor, the pressure drop changes, and that changes the liquid flow characteristics. This is, if you forget about this part, the red part, this is the normal procedure what you have done so far, what you have studied so far in fluid mechanics. Change the surface, change that so called epsilon in the Modi diagram, change your friction factor, find out what is the pressure drop, and you get the different value of pressure drop. What if now we add heat transfer at the wall? We create a bubble at the wall, we force a phase transfer at the wall, and this heat transfer is going to change the interfacial characteristics, and this heat transfer is going to affect the friction factor. So, it is not that fluid mechanics is controlling heat transfer. What we are trying to see is whether heat transfer can control fluid mechanics as well. And how it is done? If you let us think of in a simplistic fashion, if we create bubbles, a large number of bubbles on a solid surface, then the liquid, a small fraction of the liquid will not see, will not know that a solid exists at some point. So, a surface is going to be covered by nanobubbles, and the fluid, the liquid in this case, is going to slip over the nanobubble covered surface. So, what happens to the friction factor? You are going to get a very reduced value of friction factor. So, that is the concept. We wanted to see whether heat transfer, by incorporating heat transfer at the wall, by creating very small bubbles on the surface, whether or not the frictional pressure drop that we measure is going to be different or not. Okay. So, that was the experimental plan for such thing, and for which we have decided a flow visualization setup. In fact, I think I will go to this first. This is the setup which was created. Okay, an aluminum channel, and on the aluminum channel you using milling process you create thin channels. Okay, the channels are still hundreds of micron in size, about 75 to 150 micron would be their size, and the milling process was varied so as to get different surface roughnesses. We wanted to see whether surface roughness, how surface roughness will help in the bubble formation. We are measuring pressure drop at, so the flow of liquid is from, let us say, in one direction, and we are measuring the pressure drop between these 2 points, and over here there would be some sort of heater attached, which is going to supply a known heat to the micro channels. So, you have constant flow, measure the pressure drop, and start adding heat and try to measure the change in the pressure drop with increase in heat. And at the same time, you put a microscope over here and focus really down inside the micro channel to see the formation of the bubble. So, your physical observation of the formation of bubbles, the number density of the bubbles, the growth of the bubbles, how that process is linked to a change in pressure drop, a change in the friction factor, and whether or not you can say something about the heat transfer coefficient associated in such a process. So, the concept is use heat transfer to change the surface and then thereby to change the pressure drop. Some of the examples which so this is a description of the experimental procedure. So, you maintain the heat flux, change the flow rate, or you maintain the flow rate, change the heat flux, and at each step you measure the temperature, you measure the pressure drop, and see whether when you really see bubbles forming at the surface of the walls, whether or not you see a drastic change in the pressure drop, which obviously was observed in this case. And when bubbles are formed, the pressure drop decreases, initially decreases, then it starts to increase. So, one would like to know the background for decrease in pressure drop with formation of bubbles is well known. Okay. There has been theoretical papers published which predict that the a nanobubble covered layer would give lesser values of pressure drop. What was observed was that for higher roughness surfaces, if the surface roughness are quite large, then you would see that some of those protruded portion of the sidewall may go beyond the bubble covered layer and then thereby increasing the pressure drop. Okay. That is also to some extent obvious, but what would happen when you go from when you make a surface hydrophobic or make a surface hydrophilic? So, that is something which is going to be interesting. So, we focus on the microchannel and we see that micron size bubbles right over here. I am not sure whether you can, yes, you can still see it on the screen, that micron size bubbles are formed. Okay. We obviously cannot, using a microscope we cannot really see a nano bubble, but we see micron size bubbles. So, you increase the heat, increase the energy, and you can see that the number density of the micron size bubbles has increased to some extent. Okay. But the bubbles are still stuck to the surface, they do not leave the surface at this value of heat flux, and what was seen is that the pressure drop has decreased, because now the liquid no longer sees the rough wall, it slides over the bubbles. You increase the heat flux to slightly higher value, but before that just to mention, the shape of the bubble will be spherical as expected, and they remain in close proximity to the wall. The moment they get dislodged from the surface, they disappear. So, initially it was thought that it is due to that they condense back, but using a fast camera one can see that the bubbles are simply swept downstream with the flow. Well, that has its advantages and disadvantages. The moment you start to have bubbles, large number of bubbles flowing with the liquid through a microchannel, the question of clogging will appear. If your number of bubbles formed are quite large, the size of the bubble as they increase with heat flux are more, then you are going to come to a situation which is depicted in here is this: two bubbles almost touching each other. When two bubbles almost touch each other, then they clog the surface, they clog the entire channel, and the flow becomes irregular first, and the pressure drop increases by a substantial amount. So, another interesting thing is when the bubbles are swept away, this is still yet to be explained. There will be some remnants of the bubble on the surface, okay, and the remnants of the bubbles on the surface would act as nucleation sites for future bubbles. So, the future bubbles will grow from that site only, from that site itself at the same heat flux. And finally, we come to the hydrophilic surface. So, here we see that the bubbles nucleate at a relatively higher levels of heat flux, which is expected, right. If you have a hydrophilic surface, then the molecular interaction between the solid and the liquid molecules will be small or large, will be relatively large. So, if it is large, then you need superheat, extra superheat in order to nucleate the bubble, in order to make change of phase. And so, the comparatively larger heat fluxes are necessary in order to have a bubble formed at a bubble formed on a hydrophilic surface. And at higher heat flux, the number densities of the bubbles will obviously increase, but the size also increase concurrently. So, the bubbles will tend to clog the flow passage more in a hydrophilic surface than in a hydrophobic surface. And what also was observed, which is also intuitive in nature, is that the pressure drop in a hydrophobic surface, would it be higher or would it be less? If you think intuitively, the pressure drop, the pressure drop as measured by the 2 points, the two at the beginning, at the entry and at the exit, the pressure drop would be less. For a hydrophobic surface, the pressure drop would be smaller. Okay. So, the main points of this study, what was found is that it is possible to use heat transfer to change a surface. Okay. You can make a surface, you can change a surface by manufacturing method, definitely yes. You can treat the surface chemically so as to impart certain qualities to it, make it hydrophobic or hydrophilic, and all of these would change the flow. The whenever flow changes, associated heat transfer also changes. That's what we have known so far. But the novelty of these set of experiments would be to use heat transfer, and to use heat transfer so as to create a condition such that the flow changes. So, it is a reverse way of looking at things. And what was found is that it is really interesting is that using heat flux you can change flow pattern. If you change flow pattern, they are interconnected, which in turn changes the heat transfer. And the structure of the surface, the nature of the surface, they are very important for the formation of the bubbles and the overall heat transfer and pressure drop process. So, if I would like to summarize what I covered in today's class is first is more like two different philosophies of manufacturing, a bottom up process and a top down process. Top down process is more common, bottom up process is fastly catching up. It is a new technique, new way of, it is a paradigm shift in the thinking process of manufacturing something which is quite unique in nature. One is like almost atom by atom, you place one atom on top of the other as if, and to create a structure. It is extremely difficult to control. In some cases, for complex geometries, we still do not know how to create it. Okay. We can create a nano dot, but we do not know how to create a structure. So, whenever you create a structure, we are still going to depend on the top down process. So, you start with let us say a silicon wafer, protect some areas, remove something, and thereby ultimately end up with a structure. It could be a microchannel, it could be a transistor, it could be connecting wires in between, and so on. Then we spoke about the numbering up strategies, the strategies of scale up in microscales, the parameters that you need to maintain constant in such cases, and so on. And finally, with two examples, one is where you create bubbles, just create bubbles and see how the heat transfer is going to get affected, and look at the different regimes in which you have flow, how the different regimes in different regimes you can get different values of heat transfer. And second is an interesting way to change the liquid solid surface characteristics by using heat transfer. So, that is all for today's class. Thank you.